Hello and welcome to Maths and Me. I'm your host, Dr. Acute, and today we're going to be learning about the wonderful world of fractals. We'll be diving into the history, characteristics, natural phenomena, and applications of fractals in modern mathematics. So, what are fractals anyway? Fractals are never-ending patterns that are self-similar across different scales. They are created by repeating a process in a never-ending feedback loop. Fractals were discovered by Benoit Mandelbrot in 1975. He described them as being geometric shapes that, when broken up, would form smaller replica of the whole shape. While this concept had been around for centuries, Mandelbrot's realization of fractals led to the discovery of many other mathematical masterpieces. There are other mathematicians who contributed ideas to fractals, whose work, pre- and post-Mandelbrot, helped our understanding of fractal geometry. The first form of fractals to be discovered are known as Mandelbrot fractals. These are the most widely known and as a single image are known as brots. Julia fractals were discovered by Gaston Julia, whose work resembles Pierre Fatou. Fatou and Julia worked together and created what is known as the generalized Fatou-Julia theorem. Another form of fractals include Newton fractals, which were derived from Newton's method. These are quite different from many other fractals. Fractals are useful in modeling structures such as snowflakes, in which similar patterns recur at progressively smaller scales, and in describing partly random or chaotic phenomena such as crystal growth and galaxy formation. Characteristics of fractals include self-similarity, fine or detailed structure at arbitrary small scales, irregularity locally or globally that is not easily described in traditional Euclidean geometric language. For images of fractal patterns, this has been expressed by phrases such as smoothly piling up surfaces and swirls upon swirls, as well as recursive and simple definitions. Ferns are a self-similar set, meaning that they can be mathematically generated and reproduced at any magnification or reduction. The formula was one of the first to show that chaos is inherently unpredictable, yet generally follows deterministic rules based on non-linear iterative equations. This formula produced a unique fern-shaped object. Fractal dimension can be used to describe and analyze naturally occurring phenomena and objects. Natural fractals come in two forms, branching and spiral patterns. Branching types include trees, ferns, the neurons in the brain, the blood vessels in our lungs, lightning bolts, rivers branching, as well as the coastline and rock formations. Spiral fractals are seen in the Nautilus shell, weather patterns such as hurricanes, spiral galaxies, the spiral of pine cones, and sunflowers. Let's take a look at some applications of fractal geometry. Fractals are described using mathematical algorithms to explain objects that do not contain integer dimensions. This is particularly useful when applied to computer graphics, as fractals can be used to create landscapes that are otherwise impossible with conventional technology. By applying mathematical algorithms to a computer file, graphic designers are able to create the most extraordinary intrinsic and textured designs, as they now can accurately and in greater detail define the structure of our environment using mathematical sequences. An example of this is the movie Return of the Jedi, where fractals were used to create the geometry of the moon. Astrophysics use fractal geometry to study interstellar gas. This has enhanced their ability to understand the formation of stars by mathematically observing and recording the repetitive patterns of fractals in outer space. Cell phone towers and antennas now also use mathematical fractal patterning to create greater range of cell phone towers. Through their understanding of the mathematical sequences in fractals, scientists have been able to study the growth of bacteria. They can predict and analyze bacterial growth patterns. They can also define structures impossible to be defined by Euclidean shapes. Through this, they have also discovered that the basic structure of a chromosome is in fact a fractal. This has enhanced their ability to track common ancestors of species. Thank you for joining me on our fractals journey, and I hope to see you again next time for more Maths and Me.